In this part of the Computational Intelligence course related to fuzzy systems, we continue to fuzzy controllers. We will consider fuzzy rule bases and how to solve a system of fuzzy relational equations. That is, we will try to find a relation such that for each fuzzy rule, the composition of the input with this relation should produce the correct output. As the largest solution of a fuzzy rule system, we will consider the Gödel relation. And then we will consider the Cartesian product as the possible smallest solution. Assume that we are given from mu1 up to mu r membership functions of x and from n1 up to n(r) of y, and our rules in the form if mu I then ni, then it is required to find the fuzzy relation rule that fits the rule system. One solution is to find the relation rule such that for every I from 1 up to r, ni is equal to mu I composition row. So we are trying to find such a row. It is satisfying this condition. Mu composition row is a mapping from y to interval 0, 1 such that y is the supremum constant all x values such that minimum of membership value mu x and row xy, and after that, after taking the minimum, we are finding the superior. Assume that we have a single rule and we are trying to find the largest solution. The following theorem is about this. Let if A then B be a rule with membership function mu A defining a fuzzy set on X and the membership function ni B defining a fuzzy set on Y, then the relational equation ni B equal to mu A composition row can be solved if and only if the Gödel relation row A Gödel B is a solution. For this Gödel relation to be a solution, we require for each pair, xy pair, we need this equation to hold. The Gödel relation defined such that it is a relation on x Cartesian y to interval 0, 1, and it is defined as for any tuple xy, the value is 1 if the value of the membership mu on A at point x is less than equal to membership on B, ni B at point y. Otherwise, it will have the value ni B at point y. If rho is a solution, then the set of solutions, that is, these solutions are satisfying. They are element of the fuzzy sets on x Cartesian y such that they are satisfying the condition mu B equal to mu A composition rho S. Has the following property. If rho S prime and rho S double prime, these are the relations satisfying this condition, then the union of rho S prime and S double prime is also satisfying this condition. If the Gödel relation is a solution, then Gödel relation is the largest solution with respect to subset property. Suppose that we are given the fuzzy set membership mu A. It is 0.9, 1, and 0.7, and mu B is 1, 0.4, 0.8, and 0.7. Now we are trying to find out the Gödel relation by using the definition of the Gödel relation. This is saying that for any xy pair, if the membership of A at point X is less than the membership on B at point Y, the value is 1. Otherwise, it is equal to membership value on Y. And here, this is mu A and this is mu B. For each point, we are comparing the value. So here, we are comparing 0.9 and 1. Because this is smaller than 1, mu on X is smaller than mu on Y. So the value is 1. And compare this to, this one is larger, then we are choosing that one, it is 0.4. Compare 0.9 and 0.8, so this one is smaller, we are choosing the second case, it is 0.8. Compare this to, this one is smaller, this is chosen, it is 0.7. And this has value 1, always it is greater or equal to this. So this line is copied here. For the last one, we have 0.7. It is less than 1, so value is 1. It is greater than 0.4, so 0.4 is copied here. It is less than 0.8, so value is 1. And for these two are equal, so value is 1. This is the Gödel relation, so it is written here. Here a relation is given. In order to understand if this relation is a solution, we find the composition of this given membership on A with the given relation and check if it is equal to the membership on Y. Remember that for the composition, we compare each column here with the values of in the set mu A, and we choose the minimum one, and for each comparison we choose the minimum, and then we choose the maximum. So 0, 0.9, minimum is 0. Here the minimum is 1, and for this one the minimum is 0. Choose the maximum, it is 1. The value is 1 here. And compare this column and the membership on A. We have 0, and this is minimum 0.4, and for this one, this is smaller. So we have 0, 0.4, and 0. The result, the maximum is 0.4. For this column, compare 0, 0.9, minimum is this one, 0.8 and 1, this is minimum, and 0, 0.7, this is minimum. So we are choosing the maximum, it is 0.8. The last one, compare these two, this is smaller, 0.7, this is smaller, 0, again this is smaller, 0, the maximum is 0.7, we will have 0.7. Now compare this one with the value given here. Notice that they are the same. So row 1 is a solution. Another relation is given here. Again, it should be checked if this is a solution by the rule of the composition. We have to check if this condition for row 2 also is satisfied. For this example, this is also a solution. If row 1 is a solution and row 2 is a solution, then by the theorem, the union of row 1 and row 2 is also a solution. Here the union is written, union of row 1 and row 2. Remember that here the union of row 1 and row 2 is given. Notice that in order to find the union, we have to compare the elements one by one, and we have to choose the maximum one. So in the union, we will have 0, 0.4, 0.8, and 0.7. And similarly for this line, we have 1, 0.4, 0.8, and 0. For the last row, we have 0, 0, and this is larger, 0.7. So this is the union of these two relations. So we have row 1 satisfying the condition. This is a solution. This is another solution. The union is also a solution. It may be checked if the composition with the given membership on A with this relation is satisfying the membership on Y. And you will notice that if it is checked, this is also a solution. And if we compare this union with the Gödel relation, you will notice that if you compare one by one, always the value for the Gödel relation is larger than or equal to the value given here. So this is a subset of the Gödel relation. So it was by the theorem, it was saying that the Gödel relation is the maximum one in terms of the subset relation. So this is the largest possible solution. Sometimes it may not be possible to find a solution. If we find the Gödel relation, it may not be a solution. It may not satisfy the mu composition with Gödel relation, resulting in this membership on Y. However, still, it is the largest possible relation close to the solution. So, the Gödel relation is the largest solution. Row 1 and row 2 are two minimal solutions for this example. Suppose that we have multiple rules. Again, we are trying to find out the largest solution. This is a generalization of the previous result to system of our relational equations. This theorem is related to find the largest solution. Let membership on BI equal to membership on AI composition with rho. This is the relation that we are trying to find out. For I from 1 to R, be a system of relational equations. There is a solution if and only if the intersection of the Gödel relations on AI, BI is a solution. That is the intersection of the largest solutions. And if intersection of the Gödel relations is a solution, then this solution is the biggest solution, with respect to subset relation. Remark, if there is no solution, then Gödel relation is at least a good approximation. Up to now, we considered the biggest, largest solution. Now let's consider small solution. First, we are considering single rule, small solution. Sometimes it is a good choice not to use the largest, but one of the smallest solution. That is the Cartesian product on AB, the relation Cartesian product, which is the minimum of the membership on A and membership on Y. If a solution of membership on B is equal to membership on A composition with the relation rho exists, then the relation Cartesian product is a solution too. This is the smallest solution. If there is a solution, the Cartesian product is the smallest solution. We have a theorem saying that let membership on A be a fuzzy set and membership B on Y is defining another fuzzy set. Furthermore, let the relation rho be element of the fuzzy sets defined on Cartesian product of X and Y. Let this one be a fuzzy relation which satisfies the relational equation B membership on Y for the set B is equal to membership mu for the set A on X composition with rho. This should be satisfied. Then this equation holds. This is saying that membership of B for set B on Y is equal to membership of a set A composition with the Cartesian product relation. That is, if a solution exists, then the Cartesian product is a solution. When we have multiple rules and looking for small solution, Cartesian product can be used. For our rules, I is from 1 to R, we are looking for a relation rho such that this equation should be satisfied. The equation is saying that the membership for the fuzzy set BI should be equal to membership for fuzzy set AI. This is composition with the relation rho. So these are equations can be solved reasonably with Cartesian product of A and B by using the relation is the maximum of the Cartesian product of A, I, BI. I is from 1 to R. So we are considering the value over rules and then we take the maximum. Suppose that the measured value for x is x0. So for crisp value x0, element of the reference set x, this is in fact represented by 1 x0. This is the representation of crisp value x0. In that case, the value of n at point y is equal to the composition of the crisp function with our relation rho, and here at the point y as the value of the membership function n. Here, for each rule, we are considering the minimum of the crisp function x0 at point x and the Cartesian product of AI, BI at point xy. We are choosing the minimum of these two, and we are changing x, and we are finding the supremum of this minimum values. So this is the definition of the composition. And then, because we have our rules, we are finding what is the maximum over each rule. Instead of this inside, because this function has value 1 at x0 and it is 0 for another point, this is the minimum of the membership of AI at x0 and the membership BI at point y, and then we are finding the maximum over each rules. In fact, this is the Mamdani Asliyan fuzzy control, and we will see the details of the approach in the next lecture.